Hi, this is Joe Orloff. I'm presenting my final analysis for the dengue fever problem on the Driven Data website. Dengue fever is a mosquito-borne disease that occurs in tropical climates, which lends itself to an interesting predictive analytics problem due to the fact that you can potentially track mosquito behavior and thus the spread of dengue fever through climate-based variables to try and see where potential spikes in this disease will be seen and at what times based on historical data. The significance of this is due to the fact that this illness can range from feeling like the flu to being potentially deadly. Health organizations need to be able to allocate their resources appropriately to provide the necessary aid in the right times and the right places so that they can potentially stem this disease from being fatal to just being an inconvenience to the people who contract it. Moving down to the data, one of the shortcomings, I guess, of my analysis of this data is I am not an expert in climate or these areas or the migration patterns of mosquitoes, so it was a little difficult to test for outliers. And I think due to the robustness of the machine learning algorithms that I chose to use, I wasn't necessarily super worried about the algorithms, or excuse me, about the outliers. So the first and I think the most important or largest data issue that I saw was the large number of missing values in the data set, ranging from 194 missing values down to 10. So the first thing that I wanted to do was to check how many of the observations in the training data set had at least one missing value. I figured out that 257 observations in the training set had one missing value. Due to the fact that this was a relatively small number for the training data set, and I didn't want to dilute the predictive power of the model by imputing in potentially incorrect numbers, I decided to just remove those observations from the model building phase. After removing those 257 variables, I then randomly selected 80% of the data to be in the training data set and 20% of that training data to be in the validation data set. I chose to do this due to the fact that we're only allowed 3 submissions per day in the Driven Data website. So I wanted to make sure that I was only submitting models that had the strongest predictive power and potentially were the most communicable to outside data, so as to not waste my time scoring models through Driven Data that weren't going to perform well. There was also a large number of missing values in the test data set. Unfortunately, or fortunately, deleting those was not an option, so I was able to test out some new imputation methods. I again didn't want to just go with the mean because I feel like that sometimes dilutes the sample, so I decided to look into some additional imputation methods. I looked into the last observation carried forward imputation method and the predictive mean matching method. At the end of the day, I chose the predictive mean matching method because I thought this would produce the most realistic results, or the most realistic imputations for the missing variables. As you can see in this figure, this method removed all the NAs from the test data set except for the 2 in the reanalysis of the SAT precipitation amount. This was due to the fact I believe that there wasn't enough data available to impute those with a viable score. So for those 2, I just did the mean. Moving on to one more data observation is that the Y variable in this analysis, the total cases, appears to have a Poisson distribution. This was just one of many variables in the data set that didn't have a normal distribution. Due to the fact that I was solely going to use machine learning algorithms and not a linear regression model, I didn't take the time to try to transform these variables. But I think if I was fitting a linear regression model, a large number of transformations would have been required on the variables in the training data set. Moving on to the model types, the first model that I tried was a regression tree. more as a baseline model just to kind of see the results that I would get from it. I used cross-validation to optimize the tree size of the model. The model performed the best the model appears to even off in error at the tree size of 5. So I was able to optimize that model with a tree size of 5. Again, I didn't think that this model would end up being the winner, which it was not, but again, wanted to try to use it as a baseline model. Moving forward onto the random forest model, I tend to have a lot of luck with this model. I think it's a really great out-of-the-box algorithm to use due to its robustness to a lot of issues with data, its simplicity in training the model. It's just a great algorithm to go with. Very strong, usually provides a great prediction. This ended up actually being the winning model that you'll see in a little bit. I also was able to optimize this model through cost validation, or the mtry number in this model through cross validation to get an optimal value of 12. So that was a great learning experience. As you can see here, it looks to be the week of year and the year are having the two strongest impacts on the model, with precipitation appearing to have some of the lower impacts. The last model I tested was the boosted tree model. This is also usually a model that has a lot of really strong predictive power. This model was the only model that I didn't optimize through cross-validation and tuned manually. For this, I ended up choosing 10,000 for the entry parameter, 12 for the interaction depth, with a shrinkage of 0.001. The model performance you can see in this figure shows that the random forest performed the best on my test data set, my validation data set, and the driven data data set with a score of 25.8389. So this random forest model performed best on my data and the driven data scoring method, which was not the case for the midterm, so that was a good thing to see. My score put me in 448th place out of 1,786 competitors, which was the 75th percentile in the competition. I made all of my predictions using the predict function on the train, validate, and then the test data set. The limitations of the regression tree are it's more sensitive to the biased variance trade-off and requires some more data preparation. Random forest and boosting are handle those issues much better, but tend to both be a little bit of a black box solutions, and we're computationally taxing. Optimizing these models, I found actually for the first time ever to see a little bit of a slowdown in performance of trying to do that. In the future, I think I maybe could have potentially used some more time series focused data, since it looked like the date and the year appeared to be having a large factor on the number of cases from my variable importance from the random forest algorithm. But again, it would have needed to have been a time series forecasting type method that allowed outside regressors. In this, I learned how to tune machine learning algorithms with the carrot package and learn some more robust imputation methods beyond just imputing the mean value. So that was a really good learning experience for this.